Okay, good morning, everyone. Today, we are very happy to invite Dr. Wen-Sen to come to give us a talk. Dr. Lu received his Ph.D. in physics from Rutgers University this year. His thesis work focused on the realization of protective superconducting circuit with EJ junctions, and superconductors. Today, he will introduce us his PhD work. Before he came to US to pursue his degree, he served in TSMC for 2.5 years and implementing three-dimensional IC stacking technology to fingerprint sensors and smartphones. So currently, he's working on integration and simulation of noisy intermediate scale quantum devices in IBM Quantum. So let's welcome him.
Okay, thank you, Minjian, and thanks everyone for having me today. Just want to touch base. Can you see my laser pointer and also hear my voice? Okay, good.
Maybe
thank
voice can be
larger. How about this?
Yeah,
this is better. Okay. So it's my honor and pleasure to present our work on using Josephson circuit to build protected quantum bits. So my name is Wen-Sen, and this is my thesis work in Rutgers University with Professor Michael Gershen's group. I'm currently working on designing a co-simulation for superconducting quantum circuits in IBM Quantum. But before we start, I probably need to give you this disclaimer that this work was done in Rutgers and does not represent IBM's standpoint given my current role at IBM. However, I do appreciate the opportunity to participate in this particular research, where we, strictly speaking, this device and all other superconducting qubit, flux qubit, C-shunt qubit, fluxonium, heavy fluxonium, and so on and so forth, are actually on the same so-called periodic table for artificial atoms, where we can engineer the circuit Hamiltonian by changing or adding elements to give more flavor in the parameter space to play with. For example, in the transmon qubit, we change the ratio, EC over EJ ratio, to suppress the slope of the charge dispersion curve in the transmon. So we have like charge insensitivity in T1, or in this case, we get advantage by inserting extra elements to get accidental degenerate levels in Hamiltonian in order to provide additional layer of protections. So my thesis work was built around this particular superconducting circuit, Bifluxon circuit, and in particular, I focus on two main elements to realize these circuits: the Josephson junctions with low Josephson energy EJ, and a superinductor which enables large quantum fluctuations in the phase space. And I would skip the low EJ junctions in this talk, since I think most of our audience here are more interested in quantum devices rather than condensed matter physics with Josephson junctions. But in the meanwhile, I'm open to any discussions that my opinion might be helpful. So my personal opinion might be helpful. So please feel free to raise your question at any point. Okay. So this talk is planned to be 40-ish minutes. My talk will consist of two parts. First of all, the microwave response of the superconductor material called granular aluminum resonators, which we use to build this circuit, and second, the prototype of the Bifluxon qubit. So before we start, let's begin with superconducting circuit 101, which is the introduction of a single Josephson junctions. So the top left panel here shows the schematics of Josephson junctions, which is built from two superconducting electrodes separated by a thin dielectric layer, which serve as a tunneling barrier. We work with aluminum, and the TC is 1.2 Kelvin, and the dielectrics about 1 nanometer native dielectric is about 1 nanometer native aluminum oxide formed in oxygen atmosphere. The junction lithography and multi-angle deposition of pure aluminum films are shown in this panel. It's called using the so-called Manhattan geometries. The circuit diagram of the junctions include three elements. The first one is the resistive, a resistive response that's responsible for all possible losses. A capacitor formed by these paraplate structures. And the last one is the nonlinear element described by the Josephson equations, where the current through this nonlinear element is proportional to the difference of the phase of the macroscopic wave function describing the Cooper pair condensate in the two electrodes. If the current exceeds the critical value IC, a time averaged voltage proportional to the rate of time evolution of the phase, d phi dt, will be generated across these junctions. This Josephson effect constitute. Oh, is there a question?
Sorry, I have
yes.
In the top left corner figure. I'm curious. The Joseph junction is separated by 90 degrees. Is not at the two sides. Is it a common? It's just the configuration geometry. Or,
it doesn't have to be 90 degrees. It's a good question. It doesn't have to be 90 degrees. In fact, this is because of our geometry is using this Manhattan, Manhattan Street, like Manhattan Island near New York. In New York, it's like 90 degrees. But this is like in Chinese, I think called 棋盘式方格, right? But this is not necessarily the case in, for example, Dulum bridge. That's another fabrication technique used in many other groups. They just use a suspended bridge, so they deposit this way and that way. And in Dulum bridge, it's more like parallel in this sense. So it's not necessary, as long as you have overlap geometries and with oxide in between, that can be just basically it's just a pair of plate capacitors.
So when you design, does the different angle affect the resistance and capacitance you design? Is it the key part to design? How?
I mean, it is a key part for experimentalists, but I think it's not a key part for theorist, because it's simply just you have a characteristics rho resistivity, and you have characteristic like capacitance, and it scales with area. So okay. It's kind of, it's not that complicated. It's just like rho times rho equal, what is that? The R equal to rho times
okay.
rho, right?
Okay, thank you.
So just the standard physics, no, it's actually more like standard Ohm's law.
Mm-hmm. Yeah. Sure.
Okay, thank you. So where were we? Okay, so we have the Josephson effect, right, for single junctions, and so this Josephson effect constitutes this so-called washable potential model for classical Josephson junction by writing down the Kirchhoff current law of this circuit. Basically, we added all the currents, and you have the circuit equation for motion thing, and then you get a washable potential model. But this is more like just one thing, so I will not bore you with that. But anyway, there in this model we have two characteristic energy that we care a lot in the following slides and throughout the slides that I'll be mentioning. So the first one is the EC, the charging energy, that basically is defined, but it's defined as the energy of charging the junction capacitor with a single Cooper pair with charge 2e. So basically this is Q squared over 2c, but Q is 2e, so it's just definition. And secondly is the Josephson energy, which characterizes the coupling between the two superconducting pieces. And it is proportional to the critical current IC and inversely proportional. This is what experimentalists care more, inverse proportional to the normal state resistance of the junction. Basically, this is a tunnel resistance at room temperature when we experimentalists probe it, and we can scale it, we can convert it to EJ when we know the material property, for example, the superconducting band gap. And this AC response due to this effect, Josephson effect, is similar to an inductor. We describe it by this so-called Josephson inductance, where it's inverse proportional to EJ. So basically proportional to Rn. So we have a more resistive junction, we have larger kinetic inductance or the Josephson inductance. Okay, and at a temperature much smaller than Tc, the junction is expected to be lossless because most of the charge carrier are copper condensate, and the inductance and capacitance of a junction form a nonlinear oscillator. So basically, we only have EJ and EC, like this LC term. Form a nonlinear oscillator with high self-resonance frequency called plasma frequency, typically around 100 gigahertz at vanishing losses. So as I quickly summarize here, the charging energy and the Josephson energy scale for a typical junction that we will use in the experiment, for example, 100 nanometer by 100 nanometer in area gives EC about 2 Kelvin and EJ about for such transparency or the oxidation condition, the normal usual oxidation condition, we have, for example, 1 kilo ohm resistance, we have 7 Kelvin. So this will give us a sense that about once we have a potential barrier and the kinetic energy of the particle with EC, and we can kind of feel that if this particle is in a strictly classical regime, by classical I mean we have a lot of energy level in the potential well, or we're actually in a more like quantum region where the ground state energy is very close to the band, to the confining potential, where we have higher quantum phase slip rate, which I will mention right now. All right. Is there any question at this point? So far, so good. All right. So this classical Josephson picture, or the washable potential model for Josephson junctions, can be further extended by considering the discrete energy spectrum of a particle trapped in the Josephson cosine potential. This characteristic energy for a junction with normal state resistance is written down here already, and two processes can result in an escape from a particular potential minimum. So the first one is over the barrier, or the classical one. We call it thermal activated phase slip, which is not relevant in this talk, so we can safely ignore that. But it's a classical effect, basically just like thermal activation. And the second one is the quantum phase slip, or quantum tunneling through the local minimum to the next local minimum. And in both cases, the phase advances by approximately 2 pi, as known as the 2 pi phase slip. If the junction EC is relatively small, where we have many discrete levels, then this quantum phase slip can be safely ignored. However, for if we have EJ approaching EC, which means the barrier is lower and lower, then we have rather shallow potential trap in this phase coordinate. Then we need to take into account this phase slip event. By the way, this phase picture is just one side of the coin to describe a Josephson system. The other side of this picture is using the number of Qubit pairs as introduced in charge basis qubits, such as transmon qubits. So these properties of different type of superconducting qubits depends on the amplitude of the quantum fluctuations of the phase coordinate and the number of Qubit pair coordinates. So basically phi and n coordinate, which need to be treated as quantum operators. The uncertainty relation for a quantum circuit basically looks like this, where the delta n is uncertainty of the number of Qubit pairs in superconducting electrode, and the delta phi is the phase uncertainty across the junctions. And for the Bifluxon qubit that we are interested in, large quantum fluctuation in the phase is required, is desired. And this can be realized only if the electromagnetic impedance of the qubit's environment is very large. So basically, the Z of the impedance, the Z's impedance, and that surrounding the junction has to be very large in order to realize a large quantum phase fluctuation. And a benchmarking number is a number used to benchmark this resistance. This impedance is the resistance quanta, and for Qubit pair, this is around 6.5 kilo ohm. So in order to realize such an environment, there are commonly two approaches to realize such an unusual environment. So the first way is what we pursue in our lab. We use from material. We use a different type of material, superconducting material, that provide the inertia of the Qubit pair condensate. Basically, the kinetic energy in the Qubit pair condensate provides the inductance, and is called the kinetic inductance. And the other approach is using a long chain of junctions, like the one we mentioned earlier in the previous slide, that each junction have a particular inductive response, and they can give us just high kinetic inductance. Right? And both of them has some material related property, which is the band gap of the material, but meanwhile it can experimentally, basically, we just control the normal state resistance where we probe at room temperature, for example, and we can tell how much kinetic inductance it will provide at low temperature when it becomes superconducting. So in both cases, the challenging part is the parasitic capacitance must be minimized, and this figure shows here give us like a quick idea, visual idea about how difficult it has to be. So, for example, this is the result from the University of Maryland group by leading by Professor Murray Tran. The capacitance was reduced by lifting the chain of junctions into the vacuum, which basically reduced the effective dielectric constants and therefore minimize the parasitic capacitance. So after we introduce the idea of superconductor, I would like to switch gear to the protective qubits. With the advancement of the artificial atoms, superconducting circuit becomes one of the major competitors in quantum computations. But despite an impressive progress in this field, more improvement are still required to build logical qubits. These days, the figure of merit of qubit is the ratio of coherence time to the gate time. And currently, the coherence time in commercial transmit qubits is of an order of about 100 microseconds, and the longest gate time is around 20 nanoseconds. To implement these error correction protocols, this ratio must be increased further by at least 1 to 2 order of magnitude. And there are several approaches to tackle this challenging problem in superconducting circuits, and one of them is mitigating the noise by material, like improving the material or like readout circuits and stuff like that. The other direction is try to build this circuit has a built-in protections at the hardware level, and we pursue the second approach in this talk. So the idea of a protective circuit can be dated back to two proposals by Kitaev and Dukov in the early 2000s. But I would highly recommend for more like illustrative theoretical introduction on this topic I will share this slide later on, of course, so you can check this this talk by Dr. Konstantin Kolnishkov. He's one of our postdoc in our group, in my previous group, on the IBM QC40 events that he shared on this talk. But let me try to give you, at least from my point of view as an experimentalist, that's how I look at this problem, how I understand this protected qubits. So the idea was proposed that the protection of qubit coherence can be protected by spatial symmetries if the logical state of the qubit corresponding to different parity of either, for example, Cooper pairs, or as in our case, the number of fluxons in the superconducting loops, and this particular parity is protected, then the energy relaxation can be suppressed against charge noise. And furthermore, if in the meanwhile, the quantum fluctuation of the phase are made very large, the circuit can become insensitive to flux noise, for example, by inserting this superinductor. And the dephasing due to the coupling to the flux noise can be also suppressed. And basically, this constitutes the idea. If there's a way that we can turn on and off the protections, then there becomes a way that we can like when we want to talk to the qubit, we will turn off the protection, so we have maximal coupling. But if we want to keep the data to preserve it, to preserve for high T1, to pursue high T1, T2, then we'll turn on the coupling when we are not, basically decouple the system from the qubits. So that's the idea behind this protective, why we want to introduce this protection. So let me quickly walk through what is actually what is the physical mechanism in our system. So in Bifluxon qubit, the mechanism of Fluxon-Parity protections coming from the so-called Arana-Kesher effect, where the individual flux quanta can tunnel through the junctions with a not too small ratio of EJ over EC. So once we have higher, EJ close to EC, then we provide quantum phase tunneling, and then with this quantum phase tunneling, we are actually and also in the meanwhile, there are Josephson junctions separated by a small superconducting island, which is Cooper pair box, and by this Arana-Kesher effect, we're able to suppress the single Fluxon tunneling, and then we can I'll just walk through what actually happens. So we're just at like we have EJ over EC is EJ close to EC, right? And with allowing the quantum phase slip happening, and this Arana-Kesher effect is a Fluxon version in the electric field versus Arana-Bohm effect for charge moving in the magnetic field. So basically, we have two junctions here, and as a result, we have a single island of superconducting pieces, where we can actually induce some charge on top of it, and this charge with the dipole moment, it creates some electric field. And when the fluxon moving in the electric field, it can actually have constructive or destructive interference that's similar to what happened in the Arana-Bohm effect when a charge moves in the magnetic field. So in the Bifluxon qubit, there are two identical junctions separated by this small superconducting island, where we mark as CPP here, and the rate of the single fluxon tunneling into the loop through the junctions constitute these islands depends on the phase difference between the amplitude of the tunneling through either of the junctions. So and this rate depends on the charge on the Cooper pair islands. If the charge on the Cooper pair island is 1e modulus 2e, so it's 1e, 3e, 5e, for example, the destructive interference of the fluxon tunneling will suppress the single fluxon tunneling and protects the parity of fluxon in the loop formed by the CPP and the superinductor. We can therefore control such charge by experimentally applying a gate voltage VG, and we can therefore turn the parity protection on and off by this gate charge. And the challenge of realizing this Bifluxon qubit lies in the successful implementation of two identical low EJ junctions in the Cooper pair box, and the realization of superinductors that enhance quantum phase fluctuation in the circuit. And that's my main experimental work in this research. So I would like to, I think I should pause here a little bit before I jump into the result or the experimental part. Is there any particular questions I could address at this point? Yes.
So you control it on and off just by applying gate voltage to different levels, so it can be in one way, just increasing all the way, and then on and off, or you.
Oh, sorry. I think so. By 1e, I mean 1e modulus 2e. So not like I want increase 1e to 1e 3e 5e. It's not like that. It's just like I can tune like from 1e to 1e, or maybe 5e to 4e, 4e to 5e. I just switching. I just like had 2 volt experimentally. I only have 2 voltage level, and 1 voltage level corresponding to n plus 1e, 2n plus 1e. And the other level corresponding to 2NE. That's what I mean, modulus. Just like 同余, just one. Just exactly. So with that, when we have 1E, then we have protection. If we remove that electron by voltage, like VG, by another voltage level, then we have no protection. And we'll see in the. Sorry, go ahead.
So in the sense, it just is it like just increase the tolerance to 2 times, increase the tolerance? I mean, because you have mod it 1 and 2, one is protected, the other is not. So it's like the increase the bandwidth to 2 times, or
actually more like decouple the qubit from the system, from the environment, or couple to the environment. So when we have 1E, the qubit cannot see any noise. Let me try to formulate it this way. Ideally, the qubit cannot see any noise. We have 0E, then qubit will be able to see all the environment noise, but also in the meanwhile we can talk to it, because that's essentially why I bring up this T over TG, the T1 over TG thing, because it's actually like it's a trade-off. You cannot have high coherence time, but in the meanwhile you can still talk to it with fast gate time. And that's why I think that's part of the reason why we have ion trap qubit. They're very good in coherence, but they are kind of like suffer from very long gate time. But still, it's still like, if we have this figure of memory, it's still much better than organic circuit. So it's much promising from my point of view. but yeah, that's the coupling matters. How the coupling, how the qubit coupled to the system, and this is the idea that we want to have a tuning up that we can decouple the qubit from the environment, or couple it to the environment.
I see. Yeah, one more thing to check. So yes, your goal is to increase or decrease the previous slide, to increase or decrease the inductance?
Increase the inductance. The idea is we want to.
I think the previous slide, when you speak about the inductance, so all you need large inductance.
Yes, maybe I should just skip to that. I have a slide, a backup slide for that. Just quickly walk it through. I didn't. Just a quick equations that will help. So this is the I just quickly get it from Professor Moricher and his thesis back in 2012. So the idea of quantum fluctuation is, if we have two operators that are conjugate variables, for example, delta Q and delta phi, and we expect we will have this what is it? The uncertainty principle, right? So with delta phi, delta Q will be greater or equal to h bar 2 or 1 if you're experimental, if you're serious. So and these two were equal to a like at the minimum will equal to the what do we call it, the 0 point energy for a single half quanta of a photon, half quanta energy of a photon, right? And the if we just like equal everything and then set omega 0 to 1 over square root of, I should still write it, sorry. Yeah. 1 over square root LC is what we do with omega 0. The photon, if you have a LC resonator, the resonance frequency is omega 0, and so the single photon energy can be estimated like this. So you have LC here, you have LC here, and if this one equal to this one, so we have LC here, and so basically LC here, and you can basically get an idea of. Here's another equation I should take. I didn't took. So the impedance of a circuit is L over square root of L over C. Right. So basically, that's the we can kind of convert it into this. So in order to have a large quantum phase fluctuation, we need a large Z0, large inductance, and large inductance means large impedance, and large impedance means large inductance. It makes sense?
Yeah, but it's like a trade-off. If you have large inductance, your omega 0 will be very small, so that will be okay.
Excellent question. So that's why the capacitance need to be very small. So the L times C need to be constant.
I see.
So from engineering point of view, we need to provide some element that is still functioning when we are using our qubit. So for example, if the qubit frequency is 5 gigahertz, so that means this element, this circuit element we are proposing, need to at least work as intended to be, for example, like a resonator, then it should be still be a resonator at that frequency. So the frequency is usually a fixed number that engineering wise we need to fix. So L times C need to be a constant number. With large L, then we need to suppress C in order to fix at the just like what you asked.
Yeah, okay, I see. Thank you.
Thank you. Let me jump back to. All right. So, okay. All right. So I think I should continue a little bit less time. So, now let me try to dive into the result. The first result will be the microwave characterization of basically we're characterizing the material that I used to build the superconductor, and this material is a microscopically is basically we call it granular aluminum, where you see the material the red part is pure aluminum and the green part is the aluminum oxide. And this is a amorphous structure. It's not crystallized at all. I will later on. I will also walk you through how we fabricate it. But at this point, let me quickly give you an idea about the material properties on this guy. So this panel shows a quick image for our device. That the orange part is the meandered nanowire. So basically, a nanowire just like going like the snakes or serpentine, and this the entire material is a continuous film of structure looks like this, and this left panel shows the dependencies of this superconducting critical temperature on the normal state resistivity of this conducting film. So basically, what we're seeing here is the resistivity, the TC of our film is kind of has some functional dependence on the resistivity, but the reproducibility is not that good because this basically is a semi-log scale and any scattering on semi-log scale is not good. But this is what we can do, and actually this is one of the challenging part in this field with this material. It's not that stable. It has to do something to do with the fabrication, which I'll bring on soon in the next slide, actually. So in our system, when we increase the normal state resistivity of this material, we see the TC increases. And in the meanwhile, when we increase this number, as indicated by this equation here, the kinetic inductance can also be increases. However, eventually we'll hit some limit. That limit is where the material TC is too low, such that it hits the superconducting SI transition, superconductor and insulator transition barrier, that the material will simply not superconduct. So, and this upper limit in our case is around 8,000 microohms centimeter, which give us about, I think it's around 8 nanohenry per square, corresponding to that number. So as I mentioned, the challenge of preparing such structures with large kinetic inductance, including reproducible deposition, and also integration of this material with conventional aluminum circuit. In our system, because the film is grown, this film and Qubit films, Qubit aluminum film, are grown in different vacuum chambers. We had to come up with a method to remove the circuit oxide from the granular aluminum film to ensure superconducting contact with other circuit elements. So this is a slide that describes the technical details, where we use the AC sputtering of pure aluminum target in an argon and oxygen atmosphere. It turns out that a very accurate control of partial pressure of both argon and oxygens are necessary for a kind of reproducible process. Some of the deposition parameters are listed in this table, but I guess I would not bore you with this table. It's just that this is our control parameter, the regime that we can get, that we can control in a reasonable accuracy. So around 10 to 8,000 microohms centimeter. So now to test this kinetic inductance and dispersions in these films, we basically fabricated half-wavelength coplanar waveguide resonators, shown on the left panel here. By making the resonator with different lengths, we are able to multiplex those different resonators at different frequency and during the same cool down. And our experiment enables us to measure the system, to perform the measurement down to a single photon regime. And the resonance frequency and the losses have been measured by sweeping the microwave frequency across the resonance. And by following the same very common, this so-called phi rotation method, we're able to extract the quality factor. And it is the internal quality factor that we are particularly interested in, because this gives us the idea how the quality is the film and what are the loss channel or loss mechanism in our film. And also this gives us an idea if this is like a typical material that we are already aware of. So, so we extract resonance frequency and intrinsic quality factor Qi for the resonators with different widths of the central conductor. So you can see this is 7.4 micron, 1.4 micron, and down to 0.7 micron in terms of the width of the central conductor in the resonator structure. And the temperature dependencies of this Qi for resonators give us an idea down to the single photon regime, n equal to 1 and n much greater than 1, where it's around 1,000 photons sitting in the resonator for the red curve, and 1 photon for the blue curve. So the temperature dependence here, we can see that it saturates when temperature below 250 millikelvin, where above that temperature, the quality factor degraded exponentially with the temperature. So this analysis shows that the dissipation at low temperature is due to the interaction of the resonator with two-level systems, two-level fluctuators in the, excuse me, in the environment, where above 250 millikelvin, the thermally generated quality particle becomes the dominant loss mechanism. So what we did is we considered the two-level system losses at low temperature and the quasi-particle, thermally generated quasi-particle as the other source of losses. Excuse me. So we were able to reasonably fit the resonance shift and the quality factor with these two model. So this green curve shows the fit. At low temperature, the data can be fitted with the two-level system, while high temperature, the multi-spotting theory predicts a decreasing resonance frequency and quality factor due to these thermally generated quasi-particles.
Sorry, maybe I ask a simple question
Yes,
first.
please.
So, ideally, you need more photons to interact with the two-level system. So you like them to be at low temperature for large enough photon. Is that the ideal case, or the opposite?
So the idea is these photons actually saturate to interact. The photon sitting in the resonator actually saturate the two-level system such that it becomes not a source of loss.
Not a source of loss?
Yes.
So you need the photon to stabilize the two-level system, or
it's more like you excite the two-level system such that it's no longer attacking any more energy from your resonator. So by excite, I mean it's just like equally populated to 0 or 1 state in the two-level system, and you will not take any more energy from your resonator. So that's why we actually usually see higher quality internal quality factor at higher photon number. So by this and that, comparing this curve and that curve, higher photon number usually gives us larger quality factor because most of the two-level system loss is not there. But at high temperature, it doesn't matter because high temperature, the loss is basically coming from the quasi-particle, the thermally activated quasi-particle in the superconducting circuit. But at low temperature, there is no such thing, and we will see improvement of quality factor due to the increase of photon numbers.
I understand you said at low temperature your photons can excite the two-level system so that it like some resonate, so it cannot. I mean, then how it's like stabilized there. Then how can you operate them to the function you want, or you just stabilizing them?
I think the by two-level system, I mean the impurities.
Oh, impurity. Oh, I see.
Is that
okay.
what you? No, there's
Okay.
no qubit yet. There's no qubit in this here yet. This is just the. But yeah, you can actually think in that way, but more like qubit is taking away energy from the resonator, right? But in this, but what I want to emphasize, you can also think that way, but what I want to emphasize is resonator. I care about the quality factor of the resonator here. So the qubit or any other two-level system, actually they are taking away the energy from my resonator. And my goal in this part is I want to increase the quality factor of the resonator as high as possible.
So here, it's like some defect to the qubit. So you want to shift them away.
Yes, or like the qubits in this sense, qubits mode is like impurity.
Okay,
That
I see.
take away the energy. But because I care about resonator in this project, I want a high quality factor, high internal quality factor resonator. And if there is someone taking away my energy, then I need to know who it is. Is it because of two-level system? Is this because of the two-level fluctuator, or is this because of like this thermal activated facelet? Sorry, thermal activated quasi-particle. What is the loss channel? Yeah. And we want to know that because that is material-wise, material science-wise important.
I see. Thank you.
Thank you. All right. So we're able to reasonably well fitting the these two curves, and right. So as we just mentioned, we just addressed in the previous question, an increase of this quality factor with microwave power can be explained by the saturation of two-level systems in the regime where both two-level system energy level occupies almost the same probability at high microwave power, where it's about 1,000 photons. So as a quick conclusion, we fabricated coplanar waveguide geometry with a resonator made from strongly disordered aluminum film up to 2 nanohenry per square, and a factor of 100 or even more in terms of the total length of the size of resonator is achieved, and we have relatively low loss, and to make this resonator promising for a range of applications in the superconducting quantum circuits. So the last part, I guess, of this talk is about the realization of the prototype circuit for Bifluxon qubit, and a quick demonstration of this improvement on T1 by parity protection. So this micro image is our Bifluxon circuit prototype. I say prototype is because this in superinductor are actually made with Josephson junctions as a first demonstration. And before I leave this field, we're still working on using the superinductor or using the granular aluminum superinductor. Again, the reproducibility is not as good, so we're still kind of struggling. But anyway, this is the demonstration with junction superinductor, and the qubit formed by a Qubit box, and the superinductor is coupled to the lumped element LC raised out resonator. And in this circuit, we use two experimental tuning knobs. The first one is as I mentioned earlier, VG, which controls the charge induced on the Cooper pair box item, which is the key of the protection to turn on and turn off the protection. And the other tuning knob is phi external to control the sweet spot of the phase, and which comes from the phase difference across the superinductor. These are the device parameters, and they are optimized in the simulations. And the Cooper pair box was designed with low EJ over EC, as I mentioned earlier, to enable the quantum phase leap, while the Meandered junctions need to have high EJ over EC, such that we can confine the quantum phase leap only happens in this region. Basically, we want to control the Fluxon tunneling on this island. The LC resonator was made of pure aluminum, and which resonates around 6.5 gigahertz. So before we dive into the real qubit measurement, I want to emphasize one experimental efforts that we made in terms of charge sensitivity. So this device, because it involves this gate control scheme, so it's still a charge sensitive device. And the Bifluxon circuit will require reasonably well charge stability for the Bifluxon circuit. And many qubits are actually very worried by they worry a lot by this so-called quasi-particle poisoning. It's basically like when there are many like recent activities studying the cosmic rays. When the cosmic rays hit your for example silicon substrate, they generate phonons, and these phonons will interact with the superconducting the Cooper condensate and break the Cooper condensate into a straight single phonon, single electron that might accidentally tunnel onto your island, onto our island. That is the this so-called quasi-particle poisoning. Basically, it shift the gate to somewhere we don't want, and this event happened rather fast. Really, for a typical charge-sensitive device, it happens at time scale around 10 milliseconds for each jump. And in our case, we managed to introduce this so-called gap engineering to mitigate this problem. And the way we do it is by tuning the thickness of the film, such that by carefully design the aluminum film thickness, we're able to have high. So, for example, we purposely design thinner film in the middle that give a larger superconducting band gap, and therefore we can prevent we can like discourage the quasi-particle poisoning. And we observe, so in this curve, we show this kind of, I would call it achievement, that basically you see each like discontinued line here is a jump, and this unit is in hours. So in 8 hours, we have only a handful of jumps. Basically, conservatively speaking, is about 10 minutes per jump. Versus 1 jump every 10 milliseconds, as seen in many typical charge-sensitive qubits. So this is the main result of this work. The energy level spectrum of the qubit was studied in the probe-tone two-tone measurements, where the pump-tone FP induced the F01 transition. Oh, sorry, I think I should be more careful. There we also have 02 transition in this picture, so F0I. And measurement tone FM probes the dispersion shift of readout resonator, just like the typical readout, dispersion shift readout. And the spectroscopy data agrees well with the dark curve simulations, where we do the simulations. And at the charge-sensitive, at the frustration point where we have phi external equal to pi, the F01 tunnel rates, F01 is proportional to the single Fluxon tunneling rate. And as this orange curve approaching 0 at 0.5, which is phi external equal to pi, and also a gate charge equal to 1e. We have 0.5 of 2e, so it's 1e here. The 0-1 state become almost degenerate, which is a signature of this ionic catcher effect. And EJ and ECs are extracted from the fittings. From these fittings also agree well with design parameters. And the linear fit of F01 as function of flux give us the kinetic inductance about 0.17 microhenry, and from the superinductor self-resonance, which we do not show here, about 14 gigahertz, we conclude our superconductor has a impedance around 14 kilo ohm, which is well above the resistance quanta. And this is a main result, that we have the protection on and off, the main demonstration. So the orange curve here is NG equal to 0.5, which is 1e, and blue curve is the corresponding for reference, so where we extract the T1 about 12 microsecond, and this picture quickly shows us the by setting the gate charge to 1e, we have a nearly 10 time improvement in terms of T1. Although this number is not impressive, the original number, but I think that can be definitely improved in more like industry scale when we improve the materials and so on and so forth. But this is the main result. The increment of order of magnitude increment of T1 is what we want to show here in this demonstration of experiment. So I think I have one more slide actually. So so this slide shows the flux sensitivity of the T1, where we have 0.3 here is basically the Purcell limit of the radar resonator. But other than that, the flux sensitivity is kind of you can kind of see the flux sensitivity where the flux sensitivity shows the T1 is ranging from around like 1 microsec to around 10 microsec when there's no protection. But when we turn on protection, we can see that protection enables an order of magnitude increase in the T1 at any flux point. So this T1 enhancement on this blue curve can be further, this T1 enhancement of this an order of magnitude enhancement, that's what I mean, can be further increased by fabricating a Bifluxon with smaller scattering. By that I mean a better symmetry of the Josephson junction in the Cooper pair box. So so a quick conclusion, we basically build a pore type Bifluxon qubit with a junction superconductor, and we use gap engineering to promote the charge stability, and we have tenfold enhancement T1, and we observe the T1 enhancement, but it can be further increased by fabricating the Bifluxon qubits with less scattering in the Cooper pair box junction parameters. So with all that, I would like to thank you for your attention. These are my former group members that I have pleasure to work with, and I'm happy to take further questions.
Okay, thank you for Dr. Lu's very nice talk. So any question or comments from the audience? So for your last part, Bifluxon increase the T1, so it's due to the parity protection. Is it the same thing with the you say reduced scattering, or it's different thing?
Oh, okay. I think I'm not the best person to answer this because this is actually related. You mean the why the T1 enhancement can be further improved by EJ by making more symmetric junctions. That has something to do with the, I'm not sure if I have it, but I can try to see. It has something to do with the Hamiltonian. We need to break down into the Hamiltonian to see this EJ. Let's see if I have a slide. I have a slide I steal from Constantine. That this is a circuit Hamiltonian, and I think you already reduced it. So this is the ideal circuit Hamiltonian. So this is where this line come in. And if we have asymmetric EJ, let's see. Oh. All right. I don't think I can provide a short answer for that. It has something to do with the original circuit Hamiltonian. We need to see why this number is not. I mean, experimentally, it's not this one. This is for symmetric.
So I actually have a more general questions.
Yes,
so you mentioned that the current state of the art gate time is around 10 nanoseconds, and the T1 time is around 100 microseconds. Yes, this exactly this that. But is there a kind of like limit that you think you can, like the industry can push the superconducting hardware platform, that what is the optimal gate time here that overall you think the industry can push? For example, would it be possible that we could push the gate time to maybe 10 microseconds in the next decade? Or is there any theoretical limit for that?
Sorry, I just want to be on the same page. I think we want TG to be as small as possible, right? As fast as possible.
Oh, yes. Okay, I see.
And we want to push T1 as high as possible.
Okay.
And right now, this is number, yes, thank you for pointing out. This number is actually it's a little bit outdated. It is already like, 1 millisecond as proposed by this, proposed by Princeton group. They use tantalium circuit. So okay. There's a very good example where is the material scientists need to come in to help us, and they are really coming in and helping us to increase further, like making a better qubit that's with less material concerns. And they actually help us, like within this last 6 months, they already pushed this limit 10 times bigger. So right now T1 should be around 1 millisecond already for transmit qubits.
Okay.
So and the gate time, I think that's they will highly depends on the architecture. So for transmon is around 10 nanoseconds. For a different device, there will be different gate time. For example, for Fluxonium device will be different. And even in our case, protected and unprotected gate, we can only operate at the unprotected gate case. And in protected case, the qubit is highly decoupled. There's no way to have efficient gate time in this sense. So it's not very easy to answer it, but from transmon point of view, it's this number.
Okay, thank you very much.
Thank you.
I have a question not related to your talk.
Sure.
Yesterday I talked to Yao Zhenbang. He told me that you guys are working together right now. He is kind of your mentor. A little bit about update your life in IBM, maybe. What kind of subject in big direction that you are working on?
Sure, we are more like IC designer in this case. So actually I'm working on like engineering details. For example, how accurate I can make the resonator to be, and how to better interface with the quantum scientists, that when they come up with some kind of new novel geometry that can be used as a readout, like for example, they have a Josephson, like JPA, Josephson parametric amplifier, or some kind of new amplifier they need to interface with a qubit. And because we designed the qubit chip, so we know the qubit chip performance, and we provide them those parameters so they can have better idea, like how to create a auxiliary parts, or like amplifier or resonator or blah blah, or maybe even just a tunable qubit that can turn on and off the coupling, something like that, such that you won't degrade the chip in the large scale. Because qubit is actually like a computer. We have RAM and we have memories. We have logic, and you want to, for example, good communication between these two in terms of bandwidth, in terms of clock speed, and stuff like that.
Sounds good. I mean, we hope there will be more Taiwanese to join IBM. So see if we train more people.
Of course, I mean, I'm just a new person. 还是个菜鸟 but I'll see what I can hope. I'll try my best.
He is very happy to have you around. He told me.
Yeah, there is not very much Taiwanese person, and in this in IBM Quantum, there's a lot of AI scientists who's from Taiwan, but that's true that in IBM Quantum it's not that much. It's a little repeating.
Okay, thank you.
Thank you.
So speaking of materials, why are you still using aluminum as the superconducting qubit, or is there any candidate that can be substituted from the material scientists, or
Yes, that's also another excellent question. Personally, I think aluminum is just something that we think the oxide works very nice, that we thought we understand well. But as you can see from the Granular aluminum project, we understand nothing. But I think it's very like silicon oxide in the first place, where we have silicon is cheap and it's robust, and silicon oxide is also kind of nice in terms of uniform oxide. And aluminum oxide and aluminum works in a similar way. That's academically, like in the lab setting, it's easy to do. It's easy to fabricate, and it's robust. And the temperature is not the most convenient. The more convenient is niobium, of course, that you can operate above 4 Kelvin, which is a helium temperature. But at least in terms of like fridge, especially when we have blue force, this dry fridge system, 1 Kelvin is not a bottleneck. So it's still robust. The material is robust and kind of okay to work with. But in terms of industry, just like in the CMOS, right? We have silicon at the beginning, and we have silicon oxide, but eventually we need to change it to SiGe, the silicon germanium, and we need to swap the gate oxide to hafnium oxide and high-k metal gate and stuff like that. So I think academic-wise, aluminum works well, but we probably need to do better, and we need to change in the future.
I see. Thank you very much.
Thank you.
Any question or comments from the audience? Okay, if not, thanks, Dr. Lu again. Thank you.
Thank you so much for having me today. It's my pleasure.